Okay, great. So let's get started. Just people attending virtually. Hey, great. People attending virtually. Are you guys hearing me? Yes or no? And they can comment. Okay, anyways. Can you guys hear me? Those who are attending virtually. Just please a small comment. I guess they're not here.
They cannot listen.
Hello. Can you guys hear me? Okay, great. Awesome. Great. So we were talking about the normal subgroup. Let's give you a group. And H a normal subgroup. A subgroup of G. Then H is said to be a normal subgroup of G. We write H normal in G. This is definition. So I mean, if and only if. Guys, yeah. If GH is equal to HG for all G. Okay, so if every left coset is equal to the right coset. Okay, great. Now you know. Or I'll leave it to you to check the needy thing. So H is normal in G. It can only if GH, the inverse, is equal to H or all G. Okay, G inverse is just this set. You take the elements of H, you multiply them on the left by G, and you multiply them on the right by G inverse. Now, GH inverse is always a subgroup. GH inverse is a subgroup of G. And is a subgroup of G and a subgroup of G. Okay? For any G in G, that even if H is not normal, GH inverse is a subgroup of G. And you have a bijection from H to GH inverse. Okay? Okay, so do you want me to, I think that's I mean, the obvious way is that you have GH is equal to HG multiplied by G inverse on the right in both ways, that you get this. Okay? I mean, you can prove it formally. Okay? Is it clear? Yeah? Great. Any questions on this? Another proposition, always related. I think I proved that yesterday. Well, let G be a group and H a subgroup of G. Then the following are input. 1, H is normal in G. 2, X inverse belongs to H for all x in G, H in H. Again, these are very statements that are more or less just an exercise, you know, like repeating the evidence. I think I proved that yesterday in the exercise session, so you can look it up. But yeah, it would be very easy manipulation of it. Okay, I mean, you know, here means that AH is equal to HG for all GG. Okay. So basically, if I want to check the subgroup H is normal, what do I have to do? I take an element X of G and an element of H, and I multiply X, H, X inverse, and I should lie H. That's it. Okay? Let's give an example. You know, last time we gave example that if you have an abelian group, every subgroup is normal, right? Now, you know, I forgot the two easiest examples. A GBA group. Then EG is normal in G, and G is normal in G. This is obvious, right? This is obvious. So, you know what you can do here? Apply this. Let's do it this way. Let's apply proposition 2. To prove.
See those propositions and you don't prove them?
Yeah, I mean, I think I proved this yesterday in an exercise session. I think I'll post a video, but you can prove it. It's not a hard one. Okay, it's a good exercise. It's a good exercise in checking, and I think it has to do with your homework as well, right? Your homework exercise 3.2 has this proposition, so you have to do this in your homework. Something similar to this. Exercise 2.2 or 3.2, something like that. Okay. I mean, see homework. Okay, so prove that EG is normal in G. Let's use part 2. So let X be G and H belonging to EG, right? So if H belongs to EG, then H is EG. Then X, H, X inverse is equal to X, EG, X inverse. Because X and X inverse, which is EG, which belongs to EG. Hence, EG is. Now let's prove the second plane. G is normal G. So let X be in G. And H be in G. H really is the subgroup G. Then XH, X inverse belongs to G, right? Because G is a group. So G. Okay. Yeah. Are we good? Okay. Great. Now let's give another subgroup, or maybe let's give another definition. It said to be a simple group if it's only normal subgroups are Okay, so a simple group is a group that has no normal subgroups except the identity and G itself. Okay, so EG is called the trivial group. So basically, EG. Well, let's keep it. Okay. If it's only normal subgroups are EG and G. What's an example of a simple group? You've seen one? We haven't seen a simple. We definitely have seen an example of a simple group.
S2,
Pardon me?
S2,
S.
S2.
S2 is simple, very good. Other than that, what groups have we seen? What is the topic we have seen before? Cyclic groups. Now in cyclic groups, what do I know? I know that cyclic groups are abelian, right? Yeah. Now I know that for every divisor D of n, I have a subgroup with D elements of Z mod NZ, because Z mod NZ is a cyclic group, right? Yeah? Yeah, everybody? So if n is not prime, then Z mod NZ is not simple. If n is prime, Z mod NZ is simple. Example. Let me keep prime. D mod BZ is a simple group. Let's prove that. Let H be a subgroup of Z mod BZ. And by Lagrange's theorem, size of H divides P, right? Hence, H is equal to 1, or the size of H is equal to P. So H is equal to the identity, or H is a P, and set what is a simple. Okay? Is that clear? Yes.
Doesn't that mean it's simple?
Doesn't mean it has two subgroups. It has two normal if it has only two normal subgroups. Now, if the group G is abelian, normal subgroups, any subgroup is normal. So talking about subgroups in an abelian group is the same thing as sample from the subgroup. But in general, Z mod PZ has no other subgroups than one and then the identity. What about what I'm saying? 0. Let's see. So, 1, 0. Yes, sorry, yeah.
But if you look at the subgroup H, that's not zero G. H is contained in G,
Yeah.
and you know that for all elements of G, it's well, for all elements of G, DG equals what?
The H is equal to HT.
Yeah, so wouldn't that include for H, because all of the elements of H are in?
Yeah, I mean, H Z mod PZ is a normal subgroup of itself.
I've done like just like an example, like a sort of X.
Yep.
If we take subgroup X, then all the elements of X are like elements of G, and we're saying that every element of G is like has the property of this.
It's not no. It's not true that every subgroup is normal. Right? If this property is true, then this subgroup is normal. Okay? Is that what you're asking? It's not true. I mean, we gave an example last time. So I mean, in S3, for example, take S3, D is equal to S3, and H be the subgroup, the identity, and the permutation 1, 2. Okay? Look at 1, 3 times H. 1, 3 times H. So it's just 1, 3. 1, 3 times 1, 2. So 1 goes to 2, and 2 goes to 2. Right? And H times 1, 3 is just 1, 3 times 1, 3. So H is not necessary. Okay? H is a subgroup of S3. H is not. No. Okay. So it's not true that 1, 3 H is equal. It's not true that every subgroup is normal. But if the group G is abelian, then any subgroup is normal. Okay. Somebody raised their hand. Who raised their hand here? Raise your hand. Yeah, you. Oh, okay. Okay. So if G is abelian, then any subgroup is normal. Okay. Great. Now. Yeah.
This makes sense for S3, but for what is reference to simple group, will it always only have two subgroups?
It will only have two normal subgroups. Yeah.
That's the only subgroup that exists for that or zero.
For Z mod BZ, yeah, that's right.
Not okay. That would be different.
Exactly. So you might have a group that is simple, but it has subgroups, but they're not normal. Of course, they will be non-abelian, right? The groups will be non-abelian. The next simple group has order. So if you take away the Z mod BZ, the first abelian, the non-abelian simple group has 60 elements. So A5. And then the next one, the next non-abelian simple group has 168 elements. Okay, so we will see these maybe next time too, on Friday. We'll see this. And I think I'll make you prove one on your assignments. But anyways. Okay, so so for abelian groups, being a normal subgroup and being a subgroup is the same thing. Okay, so it's a good point that you might have an abelian subgroup that is not normal, but the group is still simple. Okay, great.
Shouldn't you use the other board instead?
Yeah,
Yeah, no, see.
here is this one. Okay. Now, what is good about normal subgroups? Why do we study normal subgroups? Okay, they look good. Left cosets are equal to right cosets. GH is equal to HG, or GHG inverse is equal to H for all G. Great, but why do we study them? Right? I mean, you should always ask yourself why. Yeah.
Those rules apply to many types of groups, including ones we already use.
Sure. Yeah. Very good. Very good. So they generalize somehow the things we have already seen. Yeah. In what sense? Okay. So we have seen that if I take the group Z and I take the group NZ, what is the quotient? GZ modulo NZ, right? This is the set of left cosets of NZ, right? This is the equivalence class of 0, of 1, of 2, of 3, up to until the equivalence class of n minus 1. Isn't that right? Now we have seen that Z modulo NZ is a group. I can place a group on Z mod NZ by just adding the equivalence classes. Right? 0 plus 1 mod n is 1 mod n. N minus 1 plus 2 mod n is 1 mod n. Right? N minus 1 plus 2 is n plus 1, which is 1 mod n. and I get this well-defined operation by adding equivalence classes. Now it turns out to generalize this case, I need the subgroup to be normal. So let G be a group. Here. This is let G be a group. And a normal subgroup. Then G modulo n is a group under the following well-defined binary. Okay. Pick a coset an. So I have two cosets here, right? I have cosets an, and I have to multiply it by another coset bn. Now, how do you define this? What is the natural way to define this? An times bn.
ABN squared.
ABN.
ABN. You want to say that? AB?
I was gonna say ABN squared, but does n squared make sense? I don't know.
Okay, yeah. So, okay, yeah. I mean, the idea here is that you just want to get a coset, right? So really, you need a coset times a coset to get a coset. Remember, how do you define addition modulo n? So if you take the equivalence class of 0, which is like, say here, in Z mod, let's say in Z mod 5Z. You take 3 plus 5Z plus 2 plus 5Z. What do you get? You get 5 plus 5Z, right? Which is 5Z, right? Yeah. Remember this? This generalize this thing here. Yeah.
So like this is like a composition, kind of like a composition form.
Really composition.
Since you're talking about like from n to an, n to bn, then that would be the composition of all a and b would change the elements of n.
Exactly. Yeah. So it's A times the set n, right? This is a set. Times this set, it will give you this set. So if you take an, you multiply everything by a, and you multiply bn, multiply everything by b, it's the same thing if you had multiplied everything by ab, basically.
That's like since
This is just a definition.
yeah, so like the n and the n are both projected onto n, then an and n will be projected.
What do you mean surjective?
Like it will hit every single.
Oh, okay, yeah. You can see it this way, but this is just a convenient definition to make it work. Okay. This is how you multiply sets. Yeah.
A and B are
In G, right? So
Yeah.
AB.
so A and is a left coset, B and B.
A is a left coset, Bn is a left coset, and ABn is a left coset. So what is the binary operation? You get a left coset times a left coset gives you back a left coset. Now I'm saying that this is a well-defined operation. This is a well-defined operation. Oops. Its operation is well-defined. So what do I need to show here? I need to show if A, B, C, D, or G such that A, N, is equal to Cn and Bn is equal to Dn, we need to show. What do I need to show? That ABN is equal to Cd. Okay. What does it mean? What do I need to show? I need to show what does ABN is equal to CDN. It means that, so we need to show CD inverse AB belongs to N. Okay. Great. Now, how do I show that? I have that AN is equal to CN and BN is equal to DN. What does AN equal to CN mean? Implies that C inverse A implies C inverse A is equal to N1 sum N1 in N. Bn is equal to Dn in the same way implies that D inverse B belongs to N, which implies that D inverse B belongs to is equal to N2 for some N2 in N. Great. Now, what is the thing I have here? I need to show that ABN is equal to CDN, or equivalently, or CB inverse, CD inverse AB. Did I use anything about normality yet?
No.
Did I use anything about normality? I'm just playing with cosets now. Okay, I'm just playing with these cosets. I didn't use anything about normality. So let's look at this. CD inverse times AB. What is that equal? This is D inverse, C inverse, times AB. Right? Everybody? Are we good? Yeah? Great. What can I do now? D inverse
By associating.
C inverse A times B. So far, so good. What is C inverse A? N1. So C inverse A is N1. D inverse N1 times B. Okay. Now there's a now if you could switch D inverse and N1, then you could say this is N1 and 2, which belongs to N. Right? If you could do that, if you could flip N1 and D inverse, or N1 and Z, you could say this is automatically N1 and 2 or N2 and 1, which belongs to N. But is this allowed? Am I allowed to flip like that?
No.
Well, that's G is Abelian. If G is Abelian, then I'm good, right? If G is abelian, I'm good. I can do that flipping. Okay? If G is abelian, flipping is automatically allowed. You see that? Suppose that G is abelian, then all of these commute with each other. So you can put them in any way you want. You'll just get it in one entry. Yes, sir.
I saw that you changed like the CD.
Inverse.
Okay.
So CD inverse. So what do you need to multiply CD to get 1? You multiply by inverse. Okay? Great. Now, if G is abelian, then that would be obvious. Now, how do I deal with this? Yes.
Can you conclude B and D have the same inverse or not?
D and B have,
The same inverse?
if D and B have the same inverse, then if D and B have the same inverse, then D and B are equal.
They don't necessarily be two.
Yes.
Now we need to use the fact that n is a normal subgroup.
Exactly. Now where normality comes in. Now, so what do I have here? I have that D inverse B is equal to N2. Agree?
Mhm.
D inverse B is equal to N2. So let me write here B as D times N2. B is equal to D times N2. Isn't that right? Okay. Should I write here or up? Should I write here or here? Here. B is equal to D times N2. This is D inverse N1 times D times N2. So far, so good. Yes. It's not necessarily equal to N1B. It's not B N1. It's equal. It's not so N1B is not necessarily equal to Bn. N1B is equal to B times something else in N1. But the same thing, right? This is what you're saying. Right? That's very good. So the subgroup N times B is equal to the subgroup N times B on the left. On the right, B times N is equal to N times B. But that doesn't mean every point. It doesn't mean that Bn is equal to NB for every NB. It means that B little n, 1, is equal to N2 times little b.
So they don't necessarily have the same.
They're not point-wise equal. You know, if you write them down in like line by line, so they're not one by one equal. But as sets, they're equal. Great. Well, I'm here now. Is this clear so far?
Yeah.
This is clear so far. Now I claim this belongs to N. Why is that? Where am I?
When the
Yes.
first three elements together, they are belonging to N by the rule. You know the inverse part of G. And
Exactly.
so by that meaning it's equal to some other element part of N, and then you multiply them and it's equal to the.
So okay. So you want to say that? Yes. Thank you. Great. So G inverse in 1D belongs to N. Do you agree with that? D inverse and 1D belongs to N. Because N is a normal subgroup. If N is a normal subgroup, means that X inverse belongs to N for any H and N, right? Take your X to be D inverse. X inverse would be D. And this belongs to N. And hence, yeah, okay, then we're good. Are we good here? Everybody, any question on this? Is it clear? You see where normality is key. Normality is just at the last single step. This step will make everything. Otherwise, boom. Yeah, Stella? Yeah. So what do I need is that CD inverse AB belongs to N. Agree. Now I expand that product by using the facts I've written here. Is here good? Here is good. I just replaced it. Is here good? Is here good? Why it's done? Okay, so if N is normal, My handwriting is cool, man. If n is normal in G, then
that's why I wanna
x
use
and x inverse belongs to n for all x in G and n in n, right? Yeah. Now let x be D, let x be D inverse, and n be n1. So D inverse n1 D inverse inverse is equal to D inverse n1 D belongs to n. Agree? Now this one belongs to n, and n2 belongs to n. Now n is a subgroup, so the product of these two will belong to. Is that clear?
third.
So just the circles. CT groups. Yes, Victor.
If n is just a billion and is not normal, is this also true?
No.
No.
Big S3, for example, and n the subgroup
No, but
identity
billion.
1, 2. If n is a billion, you're saying if n is a billion, not G. That's not necessarily true. If
Why
you
not?
take S3, for example, and the subgroup 1, 2, right?
Mhm.
1, 2 in the identity, then this doesn't work. What you need is that you need n1, n to commute with everything. So if n commutes with everything, then you can do that. What you want here is you want to switch immediately. That's what you want to do, right?
Okay.
You want to switch n1 and the inverse.
Yeah.
That's what you're meaning by a billion.
Yeah, but if it is a billion, doesn't that mean it's already true?
No, if n is a billion, it means that
No,
all the
it-
elements in n commute with themselves. That doesn't necessarily mean they commute with everything in G.
No, but if G is a billion,
If G is a billion, that's true. Yeah. If G is a billion,
if G is a billion, we don't need the fact that it's.
no, because if G
Can
is a
n be
billion,
can,
well,
can G be a billion and n be a billion, but n is not a normal?
no, we proved last time that every subgroup of an abelian group is a normal subgroup.
Hmm?
We proved that yesterday. Yes, not yesterday. In Wednesday, in Monday, that if G is a billion, then any subgroup of G is. Right? We proved that on. Yeah, we proved that on.
No, just prove that it's also a billion, that it's.
I think we put it somewhere. I mean, the proof isn't bad. So take any subgroup in a abelian group. Gn is just n in n. If G is a billion, then you can flip n and G. It's just okay. So it's not. Example, that any if you have an abelian group, any subgroup of an abelian group is a normal subgroup. Okay, great. What time is it? 40. Okay. Great. Any questions on this? Yeah.
It's just, I kind of to know, like, how can we show that operation is so I understand that in the sense why, why do we have to have,
So how do we come up? Equivalence classes are cosets, right? There are many different ways of writing your cosets, right? So you have to show that whatever way you write your cosets, your answer will not depend on the way you write it. So an times bn is equal to abn. A priori, this depends on the way you're writing your cosets, right? So if you change a and b, you will most likely change abn, not most likely, but you might think that you can change ab, right? Abn, right? Think of z mod nz, okay? Always take that as a nice example. So if you were to add 5 and 6 modulo 7, what do you get? Modulo 7, 4, right? Right? Now, change the 5 into something else that is the same mod 7. Let's say 12. you still have to get 4 mod 7. Exactly. It just depends on what modulo 7 this is. And here's the same. Okay, is that clear?
Can you give us a counterexample where this does not work?
Yeah. Take any non-normal subgroup, it will not work.
Can you show
Yeah.
us one?
Sure.
There's two primary.
So then let's take our favorite non-Abelian group. It's equal to S3 and H 1, 1, 2. Okay. So you have cosets H and 1, 2 times 1, 3 times H. So H and 1, 3 times H, which is 1, 3 times 1, 2, 3. And then you have 2, 3 H, 2, 3, and 1, 3. Okay. Now take 1, 3 times 2, 3. What do you get? 1, 3 times 2, 3. So 2 goes to, so 1 stays 6 and goes to 3. Right? Now, take 1, 2, 3. Man, this one will, I think. Take 1, 2, 3. So 1, 3 times 2, 3 will give you 1, 3, 2, right? So this coset times this coset will give you this coset. If this were to work. Right? Now 1, 2, 3 times, let's say 2, 3. What does that give you? So 1 stays fixed and 1 goes to 2 goes to 3 and 3 goes to 1. So these two, 1, 3 and 1, 2, 3 belong to the same coset. 2, 3 and 2, 3 belong to the same coset. Now take the product. The product of these two and these two should belong to the same coset, but it doesn't. 1, 2 is in H, 1, 2 is in this coset. And 1, 3, 2 is in this coset. So this operation is not well defined if H is not normal. Okay? Yeah, is that clear? I mean, you have 1, 3 H basically. You have 1, 3 H is equal to 1, 2, 3 H. 2, 3 H is equal to 2, 3 H, of course. But AB, what is that? CD, so CD inverse. So 1, 2, 3 times 2, 3 inverse times 1, 3, 2, 3 does not belong to H. I mean, we can see, we can check it. Do you want me to do this calculation to convince you? So I want to be sure as well. So let's so 1, 2, 3. That's 2, 3 inverse times 1, 3 times 2, 3. What is that equal? This is 1, 2, 3 times 2, 3. 1, 2, 3 times 2, 3. So 1 stays 1, then goes to 2, 2 goes to 3, and 3 goes to 1. This is 1, 2 inverse times 1, 3, 3. So this is 1, 2 times 1, 3, 2, 3. Then what do you get here? 1 stays fixed, then goes to 2, 1 stays fixed and then goes to 3. So 1 goes to 3, right? It's automatically not an H. 3 goes to 2, stays fixed. Okay, doesn't belong to H. So if H is not normal, let's say 2 goes to 3, 3 goes to 1 more. Okay? So if H is not normal, this is not this. In fact, if H is not normal, this is never well defined. So G mod n, this operation is well defined if and only if n is normal. Okay? Is that clear? So if G is not normal, then this operation is not well defined. Yes.
But there can be coincidences,
It might be so the operation will not be well defined if H is
Yeah. but there might be some cases where
It might be one element, one or two, some elements,
for example,
satisfy them.
in U4.
U4 is Abelian, so every all Abelian groups will work. Okay, great. Now let's give an example of this group. Let's say this is covered in the midterm as well. Okay, so today's lecture and tomorrow's lecture are covered in the midterm. Again, I think the midterm is on the 30th and the material stops on the 11th. So that's okay. So you can study during the break. Yes, sir. On Friday? Yeah. Why won't you?
Tomorrow is not Friday.
Yeah, but why won't you have class on Friday? No, I think we have class on Friday.
We have class on Friday.
Yeah, there is class. Is there any reason?
Yeah.
Yeah, we have class on Friday. Okay, and
What do you mean?
okay, great. Now let's give an example of a normal subgroup. Or let's give some properties. I'll prove that proposition. As you get an Abelian group, and N a subgroup of G, then G plus N is Abelian. Then you get a cyclic group, and N a subgroup of G. If N is a subgroup of an Abelian group, then N is normal. Then G mod N is cyclic. Okay, I'll prove one, and I'll leave two as an exercise. Then I'll do one more proposition. Prove one. G is Abelian, so N G is Abelian, and N is a subgroup of G. So N is a normal subgroup of G, and G mod N is a group. Okay, G mod N is a group. So G mod N is a group. Blah, 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 yeah. G1N times G2N. What is that equal? It's equal to G1 G2. N. Now G is Abelian, so G2. Oh, by the way, there's something I forgot to say. An important thing. What is the identity element of G modulo N if N is a normal subgroup? It should be a group. And N is normal in G. What is the identity element of G mod N? What is the identity coset of that thing? N, right?
What?
Then N is the identity of G mod N. Always think of it this way. Z modulo NZ. The identity element of Z modulo NZ is the equivalence class of 0, which is NZ. Right? So why is that? I mean, big G1N times N is equal to G1N times EGN. It's just G1 EG N is just G1. And what's the inverse of G1N? G1n inverse is just equal to G1 inverse times n. Okay, since G1n times G1 inverse times n is G1, right? That's clear, right? Okay, how much time? I don't have anything left down there, I guess. Oops, I owe you 1 minute, but anyways. Yes. I want to inverses itself. Well, 1, 2 times 1, 2, what is that equal to? Right, it's equal to the identity. Okay.